Dr. Tanamachi is an associate professor in the Department of Earth, Atmospheric, and Planetary Sciences at Purdue University. She earned her bachelor's from the University of Wisconsin-Madison and her master's and PhD in meteorology from the University of Oklahoma. Work focuses on severe weather, radar meteorology, and she's participated in several major field programs studying severe storms, including Vortex 2, Vortex Southeast, where she served as a principal investigator. In addition to her research and teaching, Dr. Tanamachi is an active member of the American Meteorological Society and currently serves on the AMS Board on Higher Education. She's collaborating with UCAR Comet and the Purdue Envision Center to help develop a radar meteorology course for the CometMat website. Let's welcome Dr. Tanamachi to the stage.
Hey, good morning. It's a pleasure to be here, and don't have too many direct connections. I think my closest connection to Linden State is vicariously through my former graduate student, Allison LaFleur, who's sitting there. So I got to hear a lot about fond memories of this place. And so when I got the invitation, I was originally invited to speak last year, but due to a conflict, I wasn't able to do it. And was really happy then to be re-invited this year. So it's a pleasure to be here. It's not my first time in Vermont. I was here for a radar conference back in 2018. But it's been a while, so I always enjoy getting back to New England. But I am definitely an interloper. I am here today to talk to you guys about radar, and specifically dirty radar secrets. And by dirty, I don't necessarily mean anything salacious. I'm a little short here, so I don't mean anything salacious, just things that may be kind of lurking under the surface that you don't all necessarily know about radar, but I'm going to kind of come from a vantage point that everybody's got like a basic working knowledge of how radar works. So, and I'll give you all a very rudimentary primer on that first. But even if you're a radar pro, I'm hoping you will get something out of this talk. And I've got a little bit of recent research to share with you. So, has everybody had their coffee?
Now that I have my coffee, I'm ready to watch radar. Right.
So I watch radar a lot. Radar is really my favorite tool amongst all meteorological instruments, and it is my favorite tool because it is the only tool that we have that really allows us to observe large volumes of the atmosphere quantitatively, remotely, and safely, which means we don't have to put scientists actually into things like tornadoes and hurricanes necessarily in order to get good wind observations. But before I get into the details of this, I want to go back and give you guys a little autobiography of myself. Just like our keynote speaker last night, I grew up in the Twin Cities area of Minnesota, and yeah, you can probably still hear a little bit of my accent in there. I can lay it on really thick if I want to get a laugh out of a group. But yeah, I grew up in Ramsey County, which is this sort of small tooth-shaped county just north of the main area of the Twin Cities. And when I was about 7 years old, this was in 1986, I'm home from school for summer, sitting in my basement, doing whatever kids did back in those days, not looking at phones. It definitely wasn't something like that. But 5 o'clock rolls around, the news comes on television, my dad comes running downstairs, and he's like, Robin, you have to come upstairs and see what's on television right now. And so I dropped whatever I was doing and went upstairs to our one television set. We only had 3 channels back in those days. 5 o'clock came around, everybody was watching the news. And it just so happened that there was this live tornado video being shown on television from a news helicopter at Channel 11. If I recall correctly, they weren't actually out there looking for the tornadoes. It's not like today where you have like 8 or 9 helicopters swarming around every tornado in Oklahoma. But they were out on a totally different assignment. I think they were going to view a concert or film a concert or something, and then they see this tornado come down, and they're like, okay, forget the concert, we're going to go after the tornado. So I showed this video not just because, honestly, I think it's almost better than some of the drone footage that we get today. It's right up there. I mean, the pilot was Dave, I'm going to have to look it up. I'm sorry, I'm blanking on what his name was, but he was a Vietnam helicopter pilot. So he had balls of steel, was not afraid to get really, really close to the tornado, and basically just let it draw him in while he was filming and announcing what he was seeing to 3 million people viewing in the Twin Cities area. And the tornado itself is actually quite spectacular. It's doing this sinuous helical undulations, and it was really mesmerizing. And so for me as a 7-year-old kid, especially one who had just seen the Space Shuttle Challenger blow up, which totally put the kibosh on any aspirations I had of becoming an astronaut, I was looking for something else to do with my life. And found out, okay, there are these absolutely gorgeous atmospheric phenomena out there that are waiting to be studied. In the days and weeks after this footage was shot, so KRE is the NBC affiliate in the Twin Cities. So of course, all the other NBC affiliates around the country were showing this video also. So it went viral before going viral was a thing, right? Everybody in the country saw this, and they brought in, via satellite link from Norman, Oklahoma, somebody from the National Severe Storms Lab gave an interview about the significance of what this video was showing, which was basically a type of tornado vortex structure that had heretofore only been seen in physical models at Purdue University. So, talk about coming full circle, that's where I work now, but I'll get there. And that person speaking was Don Burgess. And that was the first time I really heard that studying tornadoes is a job you can have. So after that, I was like, okay, I want that job. So set myself to studying math, physics, science, technical writing, computer programming, everything that I could find. I ended up, and fortunately I had access to some really good educational resources in that regard. Went to the University of Wisconsin-Madison for my bachelor's because that was the closest place that had a decent meteorology program. While I was in that class, I took part in a class on severe storms forecasting, and one day there just happened to be storms just across the border back in Minnesota, so a bunch of us got into a van and we drove west on a storm chase. So this is before mobile internet, before we had apps on our phones or anything, so we're just going on 6-hour-old surface obs and model output and what we could see visually. And near Benson, we pulled up on this supercell, and this is the picture that I took of my very first tornado. There on the left, just over the road, we've got a descending truncated cone cloud, and then there's a debris swirl at the surface. It was it was F1, it was wussy, didn't really damage a whole lot of stuff, but it was my first tornado. I was very, very proud of it. So just to flesh out my gateway tornado there. So just to kind of flesh out my biography, as I mentioned, did get my bachelor's degree in atmospheric and oceanic science at UW-Madison in 2001. At the conclusion of my bachelor's degree, I went into the department head at the time, into his office, to get some career advice, because I wasn't quite sure what to do next. He took a look at my transcript, and he pointed, amongst all the A's and B's on my transcript, his finger just came right down on a C in atmospheric dynamics 2. And he says, "You are deficient in dynamics. You are not cut out for graduate school." Okay, fine. I will just go to work here at UW at the Space Science and Engineering Center. And just some background, what he did not know was that semester I was in a really bad relationship with a guy who was calling me all night to make sure I wasn't with other guys. And that C was the thing that triggered me dumping him. So there's a backstory there, but that C was something that kind of derailed me for about a year. But it was a good experience working at SSEC. I got to work with satellite data that were collected by a low Earth orbiting interferometer in the tropics, looking at Saharan desert infrared signals. And after the end of that year and going to my first conference and everything, my supervisor at the time, Wayne Feltz, said to me, "So why is it again that you're not in graduate school? You do really good work. You're good at programming, you have the skills, you have the know-how. What's going on?" And so I told him, Professor so-and-so said I was not cut out for graduate school. And he's like, no, that's garbage. That's garbage. If you want to apply to grad school, and I know you want to study tornadoes, if you want to apply to grad school, I will write you letters of recommendation. So I went ahead and I applied to grad school again, after taking this sort of gap year to gather my thoughts and figure out what to do. I applied to 4 different schools. I got into all 4 of them, but I got a phone call in my office at SSEC from Professor Howie Bluestein, who was at the University of Oklahoma, who was somebody that I had seen on television back in the 80s in a NOVA special. So I already knew who he was. And here he is talking on the phone with me. Robin, would you like to come down to Oklahoma and work for me? Sure. Okay. I packed everything I owned into a U-Haul and I drove all the way down to Oklahoma, where I worked for him for almost 9 years. First as a master's student, where I got my master's in 2004, studying the Stockton, Kansas tornado of 1999. One summer, I did a brief excursion over to Japan, just to kind of cover some bills. I went over to Japan to cover their typhoon season with a private firm over there called Weather News. They're kind of like the Weather Channel of Japan. And back in 2005, there wasn't a whole lot of mobile internet here in the States. Japan is always like 5 years ahead of us as far as their mobile internet is concerned. So they were already able to watch TV shows and stuff on little flip phones on the subway. And you know, when I got off the plane, the first thing that the people at Weather News did was hand me a phone because they needed to keep in touch with me. So my job was to produce content for their typhoon season. They wanted an American storm chaser to come over and cover their typhoon season. So it was me and another guy named Jeff Lawson who did that. So that was really amazing because, you know, and if you ever have the opportunity to go abroad and like live and work in a different place where the culture is different, the language is different, you never learn a language as quickly as when you need to ask where the bathroom is in another language. So that was very eye-opening and very enriching. And it, you know, you've probably sensed my last name is a Japanese surname. I got to reconnect with some of my more distant family members down in Kyushu, and that was very, very nice. I still keep in touch with them now. So after that summer in Japan, came back to OU, worked for several years on my PhD, kind of had a couple false starts, but eventually I got it done in 2011 and studying the Greensburg, Kansas tornado of 2007, the first EF5 after the EF scale was introduced in 2007. And then I did a couple postdocs, a short one at the Center for Analysis and Prediction of Storms, and then got invited by Dr. Pam Heinzelman at the National Severe Storms Laboratory to apply for their NRC postdoc fellowship, which I did from 2012 to 2014. So it sounds like I'm moving around a lot, but it's actually just like in the same building. I'm just moving from office to office. The building is the National Weather Center there at Norman. Norman is really like the bullseye of Tornado Alley and the bullseye of tornado research. So in the interim, I had met and married my husband, Professor Dan Dawson, who wasn't a professor then. He was also a research scientist at CAPS. And we had our first kid. Danny was born in 2013. So after my postdoc ended, they transitioned me into a position at what is now OU CIRO, what was then called the Center or the Cooperative Institute for Mesoscale Meteorological Studies, which is, again, in the same building with NSSL, with Center for Analysis and Prediction of Storms. So after a brief stint there, you know, I'm thinking, okay, I have arrived, and I got to work in the same research group as Don Burgess for my postdoc, which was amazing. You know, talk about coming full circle. I had seen this guy on television when I was a kid, and then I got to work in the same research group with him. That was fun. So around that time, we had bought a house, gotten a dog, we were settling in, raising our family, and then suddenly this job ad pops up in my email for 2 tenure-track faculty positions at Purdue University. And it just so happens my husband is an alum of Purdue University, and he had always felt an inclination to go into academia and become a professor. He was a good instructor, really good at technical work and doing just kind of like research play, you know, and that didn't really fit very well with where he was working at the time, which was CAPS. So he came to me with this job ad and he says to me, you know, there's 2 openings. This is probably the best opportunity we're going to get to apply for dual academic positions. Academia was never really in my life's plans. I had heard all of the horror stories about how hard it was, how much work it was, how you would be working 80-hour weeks, and how it would wreak havoc on your personal life and everything. So I'd heard all those horror stories, but I thought, you know, I'm not the kind of person who shies away from a challenge. And after, you know, a couple years out of grad school, I felt like I was ready. So I went ahead and I put my application in, he put his application in. We both wrote in our cover letters, in our applications, we are a dual career couple. You will find amongst the stack of applications that you're gonna get for these 2 positions, you're gonna find one from my spouse. And we just wanted to be known up front that we are a dual career couple and we go together. We figured if they didn't want to play ball, it was probably not a place we wanted to work anyway, but they were open to that because it turned out the two positions we had applied for were previously occupied by Jeff Trapp and Sonia Lasher-Trapp, who were also a dual career couple. And they had just moved to the University of Illinois. So they were open to having another dual career couple coming and taking those two spots. So they couldn't openly acknowledge that we were a dual career couple, but they tacitly acknowledged it by scheduling our 2 interviews back to back, by allowing us to share a hotel room with our then 1.5-year-old son, so that while I was interviewing, my husband was taking care of the baby, and while he was interviewing, I was taking care of the baby. And we got the jobs. We were hired along with Professor Dan Shavas, so we ended up being, like a 3-for-2 hiring, cluster hire in extreme weather and climate. And after we moved to Purdue, had a second kid. So our family's established there now. We've been there for just over 10 years. So what do I actually do at Purdue? There's a lot of different misconceptions about what a professor who studies tornadoes does. And we have what society thinks I do, which is what's in the original Twister movie. We have what my parents think I do, which is Wizard of Oz. My colleagues in this Earth, Atmospheric and Planetary Sciences department think I'm this nut job who's out chasing tornadoes all the time. Undergrads think I control the weather. Grad students think I'm, the boss. But what I actually do is something more like the cat in the hat, with bouncing on the ball, with the fan on his tail, and the fish in the bowl on the rake, and trying to balance a lot of things. So I do administrative work, I do service work, I do teaching, and despite what the Indiana legislature says, it takes more than 3 hours a week to teach a class. I'm sorry, that does take a significant amount of time. I developed all my courses from scratch, basically. I inherited nothing but the title of the class in one case. I had to rebuild it from the ground up. And on top of all the stuff that I do professionally, I'm still, with my husband, and we're raising our family. We have 2 little boys. So there's my husband, that's Professor Dan Dawson. This was when we were on our sabbatical in Rocky Mountain National Park last year. So, those of you for whom I checked off that box on your bingo card, there you go, there's the proof. And my son Danny is 12, my son Paul is 9, and they are just the lights of my life. And they get it when mom disappears for a couple weeks to go out on a field program. And conversely, I also understand when my husband has to go out for a month and a half on field programs like Ice Chip or to go to conferences. They grok what I do. They understand. They get me. So getting back to the radar side of things, what qualifies me to stand up here and talk to you guys about radar? I worked with a lot of radars as a graduate student. There's a picture of me going out for Vortex 2 in 2009 with the smallest and most nearsighted radar in the Vortex 2 fleet, which was the UMass W-band radar. So W-band is 95 gigahertz, 3 millimeters wavelength, attenuates like crazy, which means I have to be right up next to the tornado in order to see it. And this is exactly what you see at the bottom there. Those are some data that I collected on Vortex 2. So as this animation plays over, recycles and plays over again, here I'll narrate it for you. Just let the tornado kind of die, fold up and die. But at the beginning, what you'll see is we're looking at the hook of the storm, because that's literally all I can see. I can't see the entire storm structure. I'm just looking at the hook from a distance of about 8 kilometers. And you'll see that the tornado wraps up. Those are rain curtains wrapping around. You see this eye open up right in the middle from the centrifuging of the hydrometeors and whatever debris was out there. It was in the middle of an open field, so it's probably just at most grass and dust that's being centrifuged out there. But I watched this tornado with my own eyeballs at the same time that we were scanning it. You notice that the sector keeps changing because I'm literally having to steer the antenna with left and right keys on a keyboard. So every scan is a little bit different. So I went back and I cleaned these data up a little bit and plotted them for you. In addition to this very finicky and crashy W-band radar, crashy both in the sense of I bumped into things, the truck into things, but also the computer would crash on it a lot. It was very finicky. But I also got to work with University of Massachusetts X-band polarimetric radar. I got to ride in Dow 5 for one field program. I got to work with the NWR05XP, which was one of the first mobile phased array radars back in Vortex 2, and points before that, I was actually the leader of that team for 2006 and 2007. As a postdoc, I got to work with KOUN, which is the experimental WSR-88D located at NSSL. And boy, when you push a button and a megawatt comes out of your radar, the waveguides hum. It's pretty cool. I also got to work with some data from the then National Weather Radar Testbed Phased Array Radar, which was the predecessor to the Advanced Technology Demonstrator. That's probably going to be the proof of concept for the phased array that's going to replace the WSR-88D around 2040-ish or so. So by the time y'all are my age, radars of tomorrow are going to look totally different. And then as a professor, I've gotten to work with University of Massachusetts again with their Skylo radar, which is a Raytheon product. And Allison knows all about that. She got to operate that for a couple seasons for me. And then I got to get my own radar at Purdue. It's called the X-band Teaching and Research Radar, which apparently people overseas find very funny because it sounds like the radar is up at the podium teaching people. But in addition to that, I'm also working, as was said in my introduction, on a radar meteorology course for the Comet NetEd website. So how many of you here have used Comet resources? Yeah. So they've changed their website since last year. If you have an old login, it won't work anymore. But I'll give you the QR code for that later. But we've dropped the first of 8 modules here in the last couple months. It's called Dual Polarization Fundamentals. And the next one, the radar equation, should be coming out literally like any day now, probably by the end of the month. They're just doing some last minute spell checking and stuff on it. But there's 8 to plan. I've been working on that on my sabbatical and for the last couple of years. So by the end of this presentation, you should be able to explain basic principles of radar operation. You should be able to identify several types of non-meteorological echoes on radar displays and explain some strategies for identifying them. So those are your learning objectives for today, so pay attention. Our current radar network is the WSR-88D, which hopefully you all are, know and love by now. And for this part, I need everybody to stand up, if that's available to you. I need you to stand up. And I want you to give me your best Charlie's Angels pose here. The radar beam is going to come out of the tips of your fingers. I want you to point at the horizon in front of you. And I want you to rotate 360 degrees around. Stand in place and stay. When you get back to the place you started from, raise your beam a little bit. Raise it 1/2 degree and turn around again. When you get back to where you started from, raise it a little bit more. Go around again. One more time. Raise it a little bit further. Go around again. All right, everybody's good and dizzy now. You can sit back down. So the point of that exercise is first to explain the volume coverage pattern of the WSR-88D. It's something called the step spiral, and that radars, the WSR-88D, can do that 24 hours a day, 365 days a year, and not get dizzy. So, and that's a great dance move that you can break out in the next part. So there's 15 elevation angles. Imagine if I'd made you go around 15 times. Up and around 15 times. So it takes about 5 to 6 minutes for that volume coverage pattern to be completed, and then it drops back down to 0.5 degrees and starts over from the beginning. So that's your typical volume coverage pattern. The radars of the future are not going to be constrained by the mechanical spinning of the antenna. They're going to be completely electronically steered. So once the radar has built up this picture of what's going on in the 3-dimensional volume above it, all that data gets transferred out through a series of tubes and wires and networks to a couple of intermediate servers, and eventually works its way through a couple of LDMs to large data management servers to your phone. So there's a couple bounces it has to take before it gets to you. Outages can and do happen. Like, look at the timestamp on the lower right there. That is this morning. I was just checking on this site. I refreshed it and everything was red. So something is obviously up with the network, at least in that instance. Usually these outages just last a couple of minutes, but a couple of minutes is time enough that sometimes the data on your phone are a little bit out of date. So for those of you who go storm chasing, this becomes critically important when you're trying to make decisions about where to target storms based on what you're seeing on your app. So here's your first dirty radar secret. The radar images on your app are by definition old, and possibly up to 5 minutes old. And this can have significant consequences if you are using this radar image on your phone to make life or death decisions about where to target and where to go. So I'm going to show you this animation, and I just need to spend a moment here to orient you to what you're looking at. The color fill here is reflectivity. The gray outline is the path of the El Reno tornado of 2013. the EF3/5, that unfortunately took the lives of Tim Samaras, Paul Samaras, and Carl Young, and a couple of other chasers who were out there, as well as a couple local citizens. There were a lot of people out there that day chasing. So just to set the context for you, this was about a week and a half after the Moore tornado of May 20th, 2013, which was an EF5 for sure. It went through Moore. I watched it happen. I was operating KOUN that day. Well, 7 months pregnant, by the way. So lots of people were out chasing. It was a Friday afternoon. The storms were really close to the Oklahoma City metro area, which made them easy to access via interstates. There were lots of storm chase tour groups out, including Tempest tours. And most of the chasers that were out there that day were beaconing on Spotter Network, which is what these green dots are. So, for each of the dots that you see on there, there's probably 2 to 3 more chasers who are not beaconing on Spotter Network because they don't have accounts. So one of these dots, I'm gonna guess, one of these 2 is me, and my husband, and 2 of our coworkers, and my pregnant belly. So the green dots are going to be chasers moving around, and as I play this animation, Skip Talbot gave this to me, by the way. He put this together based on the GPS lats and lawns of some of the Spotter Network icons. You'll see some of them move kind of non-physically, like going across fields and stuff, and that's just interpolating between start and end points. But I'm going to play this animation, and what you will see is when the tornado forms, you'll see a circle indicating where it is and what its diameter is. And watch what happens. So tornado forms. This is what you'd be seeing on your radar app. So notice between radar updates, a lot of things change. The chasers move, the tornado has moved a couple of miles. We still don't have a radar update. The tornado has now outrun the hook, and now it's back in the hook by the time we get the next update. The chasers are realizing they're in trouble. They're running away. I'm executing my escape plan. I am fleeing to the south. There are inflow jets licking the back end of my car. But notice how far outside the hook echo that tornado strength wind field gets between each update of the radar. Sometimes completely into the inflow notch. So the take-home message here is if you are using the data on your phone to pinpoint where the tornado is, and I think this may have actually happened to a couple of people, you can really get your butt kicked if you're not careful. If your eyes and your phone app, your radar app, disagree with each other, trust your eyes, okay? Now, since 2013, the Weather Service has implemented something called SAILS to obviate this issue with there being only 5 minutes updates near the surface. So prior to this, your VCPs, it would just monotonically increase the elevation angle between 0 and 15 degrees, or actually it's 19.5 degrees. So that would take about 5 minutes, 5 to 6 minutes. Now they can do supplemental adaptive interleaved scans. That's what SAILS stands for. So what that entails is somebody at the Weather Service has to turn on this mode. It'll go through the first 5 or 6 elevation angles in about 2.5 minutes, and then about halfway through the radar volume scan, it will actually stop, drop back down to 0.5, do a 0.5 degree scan, then go back up and finish the volume. So what you get is an extra 0.5 degree scan near the surface where the tornadoes are, where the hail is landing, where the microbursts are happening, and then finish the volume. The drawback of this is it slows down the scanning upstairs, which is the place that I really like to study. I like to study ZDR columns, and this slows down scanning of ZDR columns, but it's obvious that the needs near the surface for those data in and around the tornado itself are critically important for decision making on the part of the Weather Service. So this was one of the main reasons why that SAILS mode was introduced. So now if you watch storms evolving on your radar app, you'll notice the animations are a lot smoother, and this one is one of your more recent cases. I'm trying to remember which one this is, I can't read this. But the take-home message here is to trust your eyes over your app. Don't assume that just because your radar app says the radar is live, that it is like up to the second live, and don't use it to make life or death decisions. There can be network hiccups. You can enter into areas where the network goes down. If there's an active tornado going on, it's probably impacting power and cell towers. And when you're making your navigation decisions, when you're out chasing, make sure to account for the storm's motion. Now, let's move on. So, the take-home message here is not everything on the scope is going to be of interest to you, not going to be meteorological. Might be something else. It might be Bragg scatter, which is humidity gradients in the atmosphere, usually at the top of the boundary layer. You'll see these weird ripple patterns, and those are marking where the boundary layer is impinging upon the free atmosphere. There's going to be some turbulence structures there that actually show up on radar. It's a result of resonant scattering, and yeah, I don't want to get into the details of that. You can also have things like birds and bugs, which are mostly made of water and approximately spherical, so they show up on radar too. But they can help you find things. They can help you find things like fronts. So you can actually track fronts in much greater detail on radar than you can with surface ops in some cases. I lived in Oklahoma for 13 years, and every year we would have tons of people just tossing cigarette butts out their windows while they're driving, and that would start grass fires, and we would get little outbreaks of fires, especially on windy, hot days, when it was a real pain for volunteer fire departments to go and fight them. And so you could sometimes have these fires that would span many, many acres and produce big clouds of smoke. And the clouds of smoke are just like thermal updrafts. They're buoyant, you can get clouds on top, you can even get rain on top. They're called pyrocumulus. Sometimes they precipitate, and they will show up on radar as well. None of these things are meteorological. All of them can give you information about, say, the prevailing wind direction or what the boundary layer condition is like. There's something called chaff. Does anyone here know what chaff is? Okay, a few of you do. So that's a military countermeasure. You can dump it out of the back of an aircraft to confuse enemy radar. It has a long resonance time in the atmosphere as it kind of drifts and settles out. It's little metal fragments like that. Little shreds of aluminum foil, basically. You dump those out of the back of an aircraft, and it should confuse enemy radar into having the missile follow that stuff instead of following your plane. So military will dump this out of the back of aircraft on training exercises a lot, and it has a long residence time in the atmosphere. Typically, it will originate at upper levels and then kind of drift down, so you can follow it down through the different elevation angles, lower and lower until it finally settles out. But it can persist for, in this case, it's over 2 hours in the atmosphere. So not meteorological. So what's a meteorologist to do? Well, thanks to the era of dual pol, we can now look at correlation coefficient. We can now look at the correlation coefficient because correlation coefficient is one of the strongest discriminators that we have between meteorological and non-meteorological scatterers. The top 5 rows here, you can see meteorological scatterers, rain, hail, graupel, snow, and ice crystals are all above 0.9 in correlation coefficient. So 0.9 to 1, you can be pretty certain you're looking at meteorological scatterers. Stuff that isn't meteorological or quasi-meteorological mixed phase hydrometeors, so things like clutter, chaff, biologicals, scatterers, chaff, and debris, are going to have much, much lower correlation coefficient. Tornado debris in particular, because it is random in composition orientation, is going to have very low correlation coefficient, sometimes as low as 0.2. What is the correlation coefficient measuring? It's measuring how meteorological the stuff is that you're measuring. How alike are the horizontal and vertically polarized signals that are coming back to you? So if you have a question about whether something on a scope is meteorological or not, query the correlation coefficient field. In this case, we've got this meteorological echo out over, in this case, central Illinois, just south of Springfield. But over Indiana, near where I live, we have a big bloom of very low correlation coefficient echo. This is a bird migration, specifically a sandhill crane migration that's happening over most of Indiana. And because it's late at night, the radar beam is refracting and it's covering a much larger area, but there's a lot of bioscatter activity. So this is one of the best ways that you can tell whether something on the scope is meteorological or not. Now, other stuff that's not meteorological that can show up on the scope is the result not necessarily of physical objects that are out there in the atmosphere, but also electromagnetic interference.
Radar about to be jet.
Radar jamming is a problem. The airwaves are crowded, so the electromagnetic spectrum, contrary to what you might have seen in your physics textbooks, this is what it looks like to the Federal Communications Commission. And you can download this chart and print it out, bigger than this screen here if you want to. But this is how they subdivide the electromagnetic spectrum by frequency, all the way from gamma rays down to extremely low frequency radio waves. I'm just going to blow up part of it here that actually encompasses the place where our operational weather radar network lives. This is around 3 gigahertz here. So between 2.7 and 2.9 gigahertz, that's where our radar network lives. And we are sharing this beachfront property on the electromagnetic spectrum with a couple of other services. And there are services on either side. So if your bandwidth filter is not wide enough to scrub out those things, sometimes you can get interference, unwanted interference. Now, fortunately, the Weather Service and the WSR ADATs are priority users of that spectrum, so the onus is usually on the other people to avoid interference, but occasionally interferences do show up. So a couple things can happen. You can have what's called bistatic coupling, which is where you actually have another S-band transmitter at close to the same frequency, but a different pulse repetition time. And what you'll get are like these, almost like these rubber stamps, repeating echoes that extend radially outward and away from your radar that are caused by another radar hitting a storm and then part of its signal backscattering into your radar's feed horn. So they call these rabbit tracks sometimes. We see this on LOT a lot because there's a lot of electromagnetic transmissions going on and around the city of Chicago. It's huge. It's about as big as New York. So sometimes you'll see these repeating patterns out there. So when you see those, just know those are not real meteorological echoes. Sometimes they're caused by other WSR ADATs just happening to stare into each other at the same moment. They happen to swing past and stare into each other. And if the atmospheric conditions are right, you might pick up a signal from another radar, which, the fact that it's a repeating pattern tells you that the pulse repetition frequency is close to, but not exactly the same as yours. This spectrum being squeezed as much of it as it is, sometimes you have not necessarily malicious, but maybe carelessly placed transmitters that are close to the S-band frequencies that the ADAT uses. In this case, they show up on the radar as just continuous transmissions that show up as saturated radials. So you'll just have one radial that has an echo in it that just won't go away. And it's continuous in frequency and it's continuous in power. So in that case, the onus is on the owner of whatever transmitter is causing this interference to remove it, but usually the first time that they hear about it is the Weather Service calling the FCC, helping them triangulate, figure out where this rogue transmitter is, and getting them to install filters. But the cost burden is on the owner of that equipment to do it, and they sometimes take a couple of months. But they pop up all the time, according to my friends in the Weather Service. You'll get these, you'll have a clean scope one day, and then the next day suddenly there'll be one of these spikes on it. And then, okay, well, we gotta refer this to the technicians. They have to figure out who owns it. Occasionally, the sun will also cause problems. And, the sun, it drives our weather. We like the sun, right? But occasionally, the radar will happen to swing past the sun's disk. The sun is a very effective radiator of electromagnetic radiation at microwave wavelengths, and it's unpolarized and uncoherent. So you'll get a saturated radial, usually just for a minute or two, though. And it'll be pointing usually straight east or wherever the sun is in the plane of the ecliptic. So sunrise and sunset, you will see these sun spikes that point off to the east and to the west. And sometimes you can actually track where sunset is happening by just watching these sun spikes progress across the east and the west. Secret number 3, your radar beam may not be where your app thinks it is. The atmosphere is a fluid, and fluids like to refract electromagnetic radiation. And in the case of our atmosphere, temperature and humidity are some of the strongest determinants of how refractive the atmosphere is. So the denser, more moist the atmosphere is around you, the more the radar beam is going to bend back toward the Earth. This is a good thing, because it keeps the radar beam close to the Earth further than it would if there was no atmosphere. Of course, if there was no atmosphere, there'd be no point in scanning. But changes in humidity and changes in temperature are going to impact your ability to see, and it will also impact what you see on the scope. So when you look at radar scope in this case, it will tell you a radar beam height. You turn on your little bullseye and or crosshairs and you try to query what height this echo is at. It's going to give you a number. That number is based on a lookup table inside of the app that is looking up standard atmospheric refraction as a function of distance from the radar. It does not know anything about humidity and temperature gradients. It's its best first guess. Well, as you've seen in your radar classes, standard atmospheric refraction is just a special case of refraction. But in a lot of cases, we have non-standard atmospheric refraction. We can have what's called super refraction, which is where the radar beam actually bends back down toward the Earth and stays close to the Earth longer. In extreme cases, you can have what's called ducting, where the radar beam actually crashes into the ground or into ground clutter, so you'll actually see echoes from the ground. Or, I didn't have it on here, but subrefraction is where the opposite happens, where you actually have the radar beam shooting higher than you think it is, so it's actually exiting the atmosphere sooner. Radar signal processor doesn't know anything about any of this. Here's an example from Indianapolis where we had a bunch of storms moving by off to the north, and they were spreading out a giant cold pool, so we had this dome of cold, dense air spreading out like syrup across the ground and across the Indianapolis metro area. And as it passes over the metro area, you'll see a lot of ground clutter will light up here. So that's the radar beam temporarily being ducted back down into things like trees and buildings. In the wakes of large mesoscale convective systems, they leave large cold pools behind, and sometimes you will see wind farms show up hundreds of miles away from the radar. That is just a long atmospheric duct. So your radar scope, if you were to shine your little crosshairs over one of these echoes, it will tell you there are wind turbines 11 kilometers aloft, like at the top of the troposphere, and you're like, that can't be right. No, there's this huge mesoscale convective system. It's put down a giant cold pool. Probably it's just ducting a radar beam. Other things wind turbines do are they can sometimes create fake NATOs. I was looking at your local radar here the other night in preparation for this talk, and I noticed you guys have like the worst wind turbine pimple on a radar that I have ever seen. And in fact, it's got an azimuthal shear hotspot that comes and goes. And azimuthal shear is something that we use to measure atmospheric rotation. How can we find out whether a pimple on the radar is a wind farm or not? There's a public database of US wind turbines that's run by the USGS. So there's the QR code for that. You can look up any area you're traveling in. If you have an echo on there and you're not sure whether it's wind turbines or not, just hit that website, look it up. And it's got locations of all the turbines that they know about. You could also look at nearby soundings. Just looking at the skew T here, just looking at the thermodynamic diagram, what is the feature that jumps out at you the most? Say it louder. Inversion, right. Big old inversion here at the surface. So we go from 29 degrees at the surface up to about 53 degrees aloft in the space of less than 50 millibars. So there's a huge temperature inversion here. This is at Dodge City. Dodge City is like the poster child for turbine blockage. So if this one of these big ass temperature inversions is sitting there, you can probably guess that there's going to be ducting on your radar scope. Okay, I know I need to accelerate myself here. Secret number 4. You might have heard of level 2, level 3 data. Here's what that means. Radar scanning the real atmosphere, real storms, real life, real world, and what it gets back is a bunch of complex voltages which we then process. You will almost never see, these are called IMQ signals, time series data, baseband data. There's a bunch of different names for it. You can call it level 1. Unless you are a radar meteorologist like me, you will probably never have to deal with level 1. It's huge, 256 points per gate. But usually we boil that down into just the regular radar moments, the ones that we know and love. Reflectivity, velocity, correlation coefficient, ZDR, differential phase, and what's the last one? I'm blanking on it. There's 6 of them. So we get our moments data, and those are all fine and good, but they don't match up necessarily with the meteorological variables that we get out of models. And so we can process some of those into things like quantitative precipitation estimates, hydrometeor classifications, specific differential phase, VIL, precipitable water, et cetera, et cetera. Those are level 3 products, so those are value-added products. We've got lots of radars around the country that are working in their own native polar coordinate systems. We can grid everything and mosaic it together into easily ingestible lat, lon, XYZ files. Those are called level 4, or the MRMS data, things like GridRAD. And then we can have simulated radar data. Of course, your numerical weather prediction models do not have radars in them. They are just using the moisture fields in the model to guess at what the reflectivity could be. So the analogy I like to draw is this. If a storm is a chicken, bear with me here, this will make sense. If a storm is a chicken, level 1 data is like a freshly butchered chicken with all the parts still on it. Feathers have been removed, some superficial cleaning has been done. Level 2 is where you've divided this chicken up into breasts and thighs and wings, so piled them all together. Level 3 is like, a stuffed chicken Kiev that's ready to cook, so it's got some value added, just, short circuits your trip between the raw data and the actual finished product that you can eat. Level 4 is, chicken nuggets. They're homogeneous in size and composition, but they're easy to eat, easy to digest. And then our simulated radar data, I had to put this in here for my 12-year-old son, is like Minecraft chickens. They're blocky, and they're pretty crude relative to the real thing. I have 19 seconds left to talk about antenna patterns. This is going to take longer than 19 seconds, I apologize. Okay, so antenna patterns are complicated. Most of your energy is going to be concentrated in a main lobe that goes out in a preferred direction, and then you're going to have a little bit of splatter off to the sides. These are your side lobes. So your main lobe, your side lobes. Side lobes are bad, okay? Sometimes you can even have a back lobe. It'd be like if you turn on a flashlight and you've got light shining right back in your face. Going the opposite direction, then you've got nulls in between those. Antenna patterns for the WSR-88D are kind of complicated, but the main beam is a degree wide, and we can rotate that around to get kind of the 3D antenna pattern, and it shines through a volume of debris. I took this animation from the OU ARC, just to illustrate a point, which is not all of your energy is going out in the main lobe. Some of it is splattering off to the sides, and occasionally it will splatter off to the sides in ways that create what I call the final boss of radar signatures, which is or final boss of radar artifacts, which is elevation side lobe contamination. Your main lobe is pointing into the beware, or some area of the storm that's relatively hydrometeor free. However, some of your splattered energy or side lobes are actually hitting highly reflective things up aloft, like hailstones. And if those hailstones or whatever are moving in a direction that is opposite what's going on inside the main body of the storm, you could actually get a fake tornado vortex signature here. Let me blow this up. So we have a hook echo and we have a couplet. And, an uninitiated person might look at the scope and say, oh my gosh, we have this huge tornado vortex signature. We should put out a warning. Well, the authors of this paper, the fabulous Evan Bentley and Jamie Betcher, did us the favor of drawing where the forward flank reflectivity gradient is and marking where this hook is. And so you would expect to find a vortex signature in the black circle. Instead, you're finding it way out in the forward flank where there should be nothing happening. So this is why I call it the final boss, because it is creating something that looks like a tornado vortex signature in a place near where you would expect to find a tornado vortex signature, and it can behave like one too. So it can fake you out. So how do you identify these things? Well, you look at where they are. Are they inside or outside of the main reflectivity core? Second thing, you can look at the texture. A real vortex signature is going to have two opposing maxima that kind of come to a point and kiss each other in the middle. Imposter circulations tend to be a lot more blocky. If you have a piece of software like GR2, you can take a cross-section and see, is my main lobe in a relatively hydrometeor-free area, and kind of mentally superimpose where your side lobes are, and are they hitting something highly reflective, like hailstones. There's an example one of my students sent me of a really good elevation side lobe contamination. So this is the second to last. So weather radar, I hope I've convinced you, has revolutionized modern meteorology and storm chasing. It's now indispensable. I would not go out without a radar app in my pocket. But it's still a tool, and it still has sometimes errors and bad data in it. So trust it, but also verify it. Also, give yourself a wider margin. Don't let it lead you to overconfidence. Bonus secret, most radar data from the WSR-88Ds, from field programs, from TDWRs, a lot of those things are going to be free, and they're in the cloud for you to download. You paid for them as taxpayers. They are yours. Use them. Training on radar is also free. There's a NOAA radar applications course, which is one of the things that forecasters use. Comet MedEd, I'm producing a series of lessons for them. And then there's lots of software, and I've arranged this in order of in decreasing geekiness for people who want to use software to visualize and download radar data. So you don't necessarily have to shell out $250 for GR2 or $9.99 a month for radar scope. You can find pretty good free radar apps if you have the savvy to do some coding yourself. Thank you very much. Yeah, got a couple minutes for questions if anyone has some. Yeah.
Absolutely. Do you see any future upgrades occurring to the WSR88D network for waveform strategies or frequency agility that can reduce clutter?
Okay, so the question was about mitigation strategies for clutter in the current generation 88Ds. So the ROC is always going to be working on stuff like that. The Radar Operations Center in Norman, Oklahoma, they're always experimenting with stuff like that. They have their own 88D that they can use to test out things like that. So they do a lot of scrubbing of clutter data at the time series level, so the level 1 level, and then also doing it with the correlation coefficient. So you'll find like there are going to be blacked out areas on the scope that are usually from correlation coefficient filters. But for the most part, we've kind of finished with upgrading the 88Ds. We're kind of limping them along until the next generation of phased arrays is going to come online here in hopefully the early 2030s, maybe around 2040. But at the moment, there's always going to be work to improve the clutter filters that we have. As to specifics of how those work, generally they're at the time series level, not necessarily with the waveform. The waveforms are pretty much set. Other questions? Yeah.
A lot of the radar artifacts mentioned in your speech, taking place, on like flat kind of surface like integrated planes. As someone who might be interested, for example, chasing the event in Pennsylvania and Maryland tomorrow, where you have like those rolling hills in Pennsylvania and Maryland, are there any special radar artifacts in an environment like that that people should be aware of?
Okay, so chasing in complex terrain and using radar to do that. The best advice I can give you, if your app or your software has some kind of topographic overlay, turn that on, because that will tell you where there's going to be hills and blockages. And if you have questions about whether something is a hill or a blockage, you would query that topographic layer then to see if that's actually happening. That can also tell you about places where your radar data is going to be suboptimal. Let me just turn on radar scope right now here and take a look at what's happening. Well, that's in Minneapolis, that's where my parents live. But let's go ahead and let's look at the area that you mentioned. Yeah, just right off the bat, I can see a lot of clutter here. So one of the ways you can kind of, if you don't have time to turn on a topographic overlay, I've got mine on here, you can tell things that aren't moving and things that are in correlation coefficient are really, really low. So we have like these blue and gray and noisy patches here. Those are probably not meteorological. So then you can mentally scrub those out. If you want to know where there's blockages, the best advice I can give you is to look at, this will come up here, and this operational product viewer. Some good music going on next door. So bring up the multi-radar, multi-sensor system, and you want to look at, I'm having trouble reading this from this language here. What's called the Radar Quality Index. So which ranges from 0 to 100%, 0 being totally blocked and 100% being very good coverage. So you can look at that and you'll notice that, out west, in places out west, I zoomed in too far. Places out to the west, we've got lots of blockage out here. What's that from? Mountains, right? Yeah, so you've got whole pie wedges here that are cut out that you can't see. So just being aware of where the blockages are. This map gets updated periodically every 10 minutes or so that accounts for things like radars going down or having certain sectors blocked temporarily. Like they'll update this every 10 minutes. Yeah, George.
What is your favorite radar app to use?
My favorite radar app to use personally, I like RadarScope, but I also, my university pays for it, so. But I find it extremely useful because it was programmed by somebody who actually knows something about radar engineering and is able to integrate a lot of useful overlays and different features into it. Also, they have been open to me contributing stuff to them. So, I'm trying to bring up some actual echo here. It's being slow this morning. I love RadarScope except when it takes a really long time to load things. So this color map, you might notice, is not the standard RadarScope color map. And if you change, where is it, colors, reflectivity. If you pull down, and this is available in the mobile app as well, you can change the color maps to a variety of them. And there's a bunch that I have added that are actually friendly for colorblind people. Because 8% of men and 0.5% of women are colorblind in some form or another. So I've had them integrate color maps that are actually colorblind friendly because the native NWS color maps are not. I mean, whose idea was it to have the velocity color palette go from red to green, right? So instead, if you want to look at velocity, no, you are not velocity. You are not velocity either. Sorry, I'm having a tough time seeing at this angle. Oh, and now it crashed. Anyway, I put in a color map that it goes from red to blue instead. So I happen to like RadarScope a lot, but I know some people swear by Radar Omega or there's other ones out there on the block. So you can play around with usually free trials on most of them and find the ones that you like. I just happen to like RadarScope quite a bit, but I also am kind of biased in that way. Yeah, Mike. David, sorry.
Oh.
Yeah.
I'm enrolling in a storm chasing class at SUNY Oswego for the summer, and I was just curious. I know you mentioned chasing in the beginning part of your talk, and if you had any advice for first-time chasers to get the most out of the experience.
Okay. It's not all about the tornado. You want to enjoy the camaraderie that you're having with the people that you're going on the trip with. You want to enjoy traveling into new parts of the country and seeing sights that you haven't seen before. You're going to get spectacular pictures of storms almost no matter what. You're going with Professor Steiner, right? Yeah. He's going to find you some good-looking storms. And it doesn't always have to be tornado. It could be a photogenic hail shaft. It could be just cumulonimbus. It could be overshooting tops. You're going to see all kinds of clouds and lightning and phenomena that you've never seen before. So just be open to that experience. Also use it as an opportunity to hone your forecasting skills. So make a forecast at the beginning of the day, write it down in a notebook, and then as you go throughout the day, make notes about how things are progressing, and at the end of the day, spend 15 minutes reflecting on how accurate your forecast was and what you learned from it, what was right, what was wrong, and how you're going to change it in the future. That's my advice. What other questions do you have?
We have time for probably one or two more questions.
Yeah, one or two more. Go ahead.
So one of the big problems with the current generation of radars is obviously there's a lot of blockage due to mountains and stuff, but also there's a lot of just a lack of data because radars are really far apart. You can see this kind of in Texas and also in the Northwest. I was wondering if there are maybe plans to mitigate that out of this generation or the next generation of radars.
Yeah, so the answer to your question is yes. Just looking at, so you're pointing out there's some places where the lower atmosphere is not being well observed in, for example, North Texas. So North Texas, in fact, has a network of what are called CASA radars, which are smaller X-band gap-filling radars that are run by the local council of governments. Not every state has those, but they're kind of like a mesonet for radars. And so we're hoping that the next generation of radars, what the program is called Radar Next, that the Weather Service is running, it's probably going to be a mixture of the 88Ds being replaced by phased arrays, which are also S-band, but then having some C-band and X-band and other smaller radars kind of in the mix there to fill in some of these gaps. So, you could be part of that initiative too, as a young person. If you get involved in radar meteorology and engineering, just informing the next generation of radars, I think is going to be y'all's job. I'm working with the people who are deciding on the parameters for the Radar Next program, but yeah, I literally just came from a conference where we were talking about that and just trying to exploit other radars that are out there to fill some of these gaps.